Hello, everybody. I'm Jan Lenders. I am working for Chemours as an application development manager, and I'll be talking today about responsible manufacturing of PEM membranes, proton exchange membranes for electrolyzers, to advance the hydrogen economy. Chemours produces the Nafion brand, so for all who are familiar with Nafion, this is made by Chemours. I'll be talking about three topics today. So first, about Chemours and our role in the hydrogen economy. Second, about the responsible manufacturing of fluoropolymers. And then third, on circularity and recycling of these polymers. Who is Chemours? We are a market leader in three different segments. So in the titanium dioxide, which is used for paints, etc. Second, a market leader in thermal solutions, so like refrigerants, the Opteon or the Freon brand are well-known brands from us. And then third, a market leader in advanced performance materials, or what's also known as fluoropolymers. Fluoropolymers or advanced performance materials, they help to solve our society's biggest challenges. And how do they do this? It's by combining a lot of interesting properties. Like most fluoropolymers are resistant to corrosion. They have electrical properties that are excellent. They have high purity, which is often another reason to choose for fluoropolymers. And they can resist temperatures while maintaining a mechanical integrity. Why do people choose for Nafion in electrolyzers? It's because of our excellent chemical durability, the thermal and mechanical stability that we have, and we are working on new membranes where we modify the conductivity and the permeability of the membranes to optimize for use in the hydrogen economy. Lately, there has been a lot of word around PFAS, and fluoropolymers is basically a subgroup of PFAS. And it's important to understand that fluoropolymers are safe during their intended use. Why do we say they're safe for their intended use? It is because they don't have long-range transport potential. They're not mobile in the environment. They don't accumulate in plants or in living organisms. They don't have ecotoxicity, and basically, to sum it up, there is not really an effect on human health. Why? The fluoropolymers are persistent, and this is by design. They're made durable, and this is why customers choose a fluoropolymer, because they cannot choose for another polymer. Because the conditions where they're used are very harsh, very high temperature, etc. So, to conclude, fluoropolymers are polymers of low concern, also by the OECD, during their use phase. And next, I'll be talking also about responsible manufacturing and the end of life of those fluoropolymers, and how we can make the whole life cycle responsible. Fluoropolymers are used everywhere in our clean energy transition. So they're used in your photovoltaics to make them last longer. They're used in the wind turbines to prevent corrosion. They're used in flow batteries or lithium-ion batteries. They're used in hydrogen production, obviously the PEM membranes where I'm talking about today, but also in alkaline water electrolysis. A lot of tubes are for example, coated to prevent corrosion from the hot KOH. And the KOH itself is also made by a Nafion membrane in a chemical process called the chloralkali process. So everywhere in the industry, you need fluoropolymers to enable the clean energy transition. And finally, I want to conclude. If you think about fluoropolymers and think about the potential ban on PFAS, a potential ban for example, the industrial machinery, which means that you can't make certain sensors anymore. This will impact all the other industries. You won't have the sensors for your transportation. You won't have sensors for your chemical industry. So it's very complex, and simply saying we ban this here or there will have an impact on all other areas of our life. Next, I'll talk about responsible manufacturing. So I just covered that fluoropolymers are safe during their intended use. How can we make these products in a responsible way to minimize our environmental footprint? Chemours has committed in 2018 to 10 corporate responsibility goals, and 3 of those goals reflect on environmental leadership. We have committed to reduce our CO2 emissions by 60% going towards 2030, and beyond 2030 we want to go to net zero. Second, we have committed to reduce our fluorinated organic chemical emissions in water and air by 99% or greater. And we are the first and only company to make this public commitment until now. And then finally, waste. Reducing your waste can also help reducing your environmental impact, and reducing our landfill volume intensity by 70% will have a big contribution in our sustainable way of manufacturing. To name a couple of examples of these investments, we have invested in Fayetteville, where we make the Nafion product, for more than $400 million. We have succeeded to reduce our FOC, the fluorinated organic chemicals, in the water with 97%, and in the air with more than 99%. And next investment to help the green hydrogen economy will be in Villers-Saint-Paul, which is the plant in France. And we will invest more than 200 million to produce also Nafion polymer there, with the same abatement technologies as we're using in Fayetteville nowadays. To come back on the CO2 emissions, we have committed to reduce our CO2 by 2030 with more than 60%, but we already achieved this last year. So that is 7 years ahead of the schedule. This is something that we're extremely proud of, but we're not stopping here. We are on a path to net zero by 2050. So we had responsible manufacturing. We had safe during intended use. What do we do with the product's end of life? To think about end of life, it's important to understand what is circularity, because we can think about recycling, but that's only just a very small part of this circularity concept. Circularity is about keeping your machines, your polymers, everything you produce to keep those products in use as long as you can, and use them in the highest value as possible. So when you start thinking about making an electrolyzer, you first have to think, do I need all these materials? Refuse what you don't need, because that can be used somewhere else and you reduce your environmental footprint that way. You have to also rethink how you use your materials and reduce the amount you need. For example, if you make an electrolyzer with a membrane that's 1 square meter, but you only use the active area of half a square meter, you could think about reducing the inactive area to reduce how much you need, reduce the environmental footprint in that way. Once the material is used, you have leftovers from production, which can be reused. And we have an example of that in our manufacturing area. We will reuse all virgin material, or not all, but we try to reuse as much virgin material that we have to reduce the amount of raw materials that we need for making new materials. Then you can start thinking about repairing or refurbishing, for example, materials that you get back from your customers. Or if you go to the complete end of life, the system is gone, it's not working anymore, you can start thinking about recycling of your polymer. And this is something that Chemours is working very hard on to accomplish for the Nafion product line. Recently, we have engaged in a consortium in the US, which is called H2CIRC. And this is a very busy slide, but if you look at the left, the goal of the consortium and our partners is to disassemble the stacks in an automated way. We will disassemble the membrane electrode assembly, so with the catalysts onto it, and separate the catalysts away from the ionomer. Then the catalysts are recycled, the ionomer is recycled, we make new MEAs, and we build them in a new stack. This is the goal of the H2CIRC project. How can you recycle a fluoropolymer, a Nafion polymer? Well, we have 3 strategies for that. So the number 1 on the right-hand side is the smallest green circle. This also requires the least energy. So this is our preferred path. So when the membrane is used, we need to understand if the polymer is degraded and how much is it degraded. Can we reuse it as an ionomer, redisperse it, and make a new MEA out of it? If we learn through this project that this is not possible, we have 2 alternative ways. So we can go back to the monomer and feed it into our new monomer and polymerization line. Or third, we could go to the raw building blocks of the fluoropolymers, which is HF or calcium fluoride. And the goal of this project is to recycle more than 75% of the ionomer end of life. So we have, this is what we, the previous slide was what we are trying to do for the hydrogen economy, but for the chlor-alkali economy, we already achieved some recycling. So for those who don't know, a chlor-alkali membrane is a very complex composite with a lot of different materials in it. So it starts when you get the membrane back, it's filled up with all kinds of impurities, and you have to separate out all the composites from the structure of the membrane. We succeeded in that, and the next step is to get out all of the metals, because the Nafion membrane is attracting the metals very hard because it's an ion exchange membrane. So we succeeded in removing all the components from the composite. We succeeded next in making the used Nafion polymer purified, and then even purified it beyond our normal procedures to make a new recycled Nafion dispersion, which can go back into a new application. And this is a proof of the technical feasibility of recycling Nafion ionomer just in the simple way, the first option. And this is what we now want to extrapolate to the hydrogen economy, so we can make a sustainable hydrogen economy altogether. So thank you all for your attention. We have a meeting room at C158. So if you want to meet with us, talk with us about responsible manufacturing and how you use these membranes in a responsible way, don't hesitate to contact me or my colleagues via the app. Thank you all.